Hello everyone. So today we are looking at a problem involving polynomials in calculus, and this is actually quite interesting because we're going to be using a theorem or like a result, you can say, maybe even an observation, to be honest. But it's actually a standard result, so you may have seen it before, but a direct application of that result is usually not seen. But this is a rare example of that, where it is it's actually very helpful, and you can actually solve it in many ways. But if you actually know this result, then the problem becomes very easy. Actually, let's just see how we can deal with that. So yeah, this is the problem number 5 from the CMI Chennai Mathematical Institute entrance exam in 2016. And in this video, we're going to be looking at an interesting result involving polynomials in calculus, then obviously a proof of the result, and after that we have some book suggestions for ISI and CMI, and at the end, of course, a similar but challenging problem.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
So this is what they're telling us. We need to find a polynomial, so one of them, px, that satisfies the following conditions. When p of x is divided by x is per 100, the remainder is 1. And the second is that when p of x is divided by x minus 2 whole cube, the remainder is 2. So whenever you see this thing of a remainder, what comes to mind? Obviously, remainder theorem is probably something that comes to mind really quickly, right? You see a polynomial, you see certain p of x, certain things like x is per 100, x minus 2 whole cube, maybe remainder theorem is going to be used. And yes, it will be used, but not in the first step. So yeah, let's see what we can do with that. Now I'm going to write a lemma. So my lemma is that if f of x leaves a constant remainder c, or you can just call it anything, it leaves a constant remainder, let's say m, when divided by x minus c raised to the power k, then that implies that f prime c is divisible by x minus c raised to the power k minus 1. And actually, an interesting thing is that the converse is also true. Okay, so the converse is also true. And so this is the kind of like the result of the theorem that I was talking to you about. And let me just prove this in brief. So the proof is actually quite trivial. So they're telling us that f of x leaves a constant remainder m when divided by x minus c raised to the power k. So essentially, using the division algorithm, I can write the dividend as the divisor times the quotient plus the remainder, right? You must have seen this before. And if I just try to calculate f prime x, what would be f prime x? Right, f prime x would be nothing but d by dx of q of x times x minus c raised to the power k. And if you're aware of the product rule when it comes to derivatives, you would be able to compute this. This would be q of x times x minus c raised to the power k minus 1 plus x minus c raised to the power k times q prime x, right? And how can we kind of simplify this a little bit? So I can just manipulate this in this manner. This I can write as x minus c raised to the power k minus 1 times q prime x times x minus c, right? And splitting this up into k minus 1 and 1. So f prime x essentially then becomes x minus c raised to the power k minus 1. If I take that common, I will be left with q of x plus q prime x times x minus c. So we can actually see that x minus c raised to the power k minus 1 divides f prime of x, and this theorem is hence proven. That's what we wanted to prove. Now the converse is also true because of the fact that, in a way, integration and differentiation are inverses of each other. So if you actually integrate f prime of x, you would get x minus c raised to the power k plus some constant m that we were referring to earlier. So you can actually prove that the converse is also true. Now let's come back to the problem. What was the problem telling us? So now that we have this lemma, the problem was telling us that when px is divided by x is per 100, the remainder is 1. So this is a constant remainder. Okay, excellent. When p of x is divided by x minus 2 whole cube, the remainder is 2. Again a constant remainder. So maybe it's a good, it might be a good thing to actually apply this lemma. So it is actually saying that px is something like qx times x is per 100 plus 1. And at the same time, px is, let's say, something else, r of x times x minus 2 whole cube plus 2. Right? That's essentially what it was saying. The remainder is 2. Now we essentially now can say that p of x is divisible by x is power 99, p prime x, right, from this theorem that we just stated. And similarly, x minus 2 whole square should also divide p prime of x. So now what can we conclude from here? Now I can essentially conclude that p prime of x will be nothing but a times x is power 99 times x minus 2 whole square. Right, and that's actually great because now it's actually solvable. So I can write p prime x as a times x is power 99 x square minus 4x plus 4. And let me just proceed with a little bit of simplification. P prime x is a x is power 101 minus 4x is power 100 plus 4x is power 99. After this point, we do nothing but integrate both sides. So if I just integrate both sides, I'll get p of x is equal to a times x is power 102 by 102 minus 4x is power 101 by 101 plus 4x is power 100 by 100. And if you're having any doubts what I'm doing over here, it's nothing but the integration of x is power n dx, which is nothing but x is power n plus 1 divided by n plus 1. That's essentially what I'm using over here. And obviously never to forget the constant of integration. It's an indefinite integration, we can never afford to forget that. So now we have an expression for p of x. So p of x is nothing but a times x is power 102 by 102 minus 4x is power 101 by 101 plus 4x is power 100 by 100 plus b. Right? That's essentially what we had found over here. Now it is given to us that p of 0 is 1. Why? Because we are dividing it by x is power 99, and using the remainder theorem we essentially put x equal to 0. Right? This is essentially a little bit of the remainder theorem, which you might have maybe looked at earlier. Right? You divide by x is power 99, the remainder is 1, and you divide it by x minus 2 whole cube. So you put p of 2 and you get the remainder as 2. So now you have the value of p of 0 and p of 2, and that should be enough to find a and b. Let me just do that for you. If I put x equals to 0, I'll get p of 0, which is 1, which is a times everything becomes 0 over here, plus b. So therefore b is equal to 1. And after that, if I put x equals to 2, I get p of 2, which is 2, which is a times 2 raised to the power 102 divided by 102 minus 4 times 2 raised to the power 101 divided by 101 plus 4 times 2 raised to the power 100 divided by 100 plus 1. So we can essentially find out the value of a very easily. So a times this entire quantity, 2 raised to the power 102 by 102 minus 2 raised to the power 103 by 101 minus 2 raised to the power 102 by 100 is nothing but 1. And then you can really find out the value of a. You can simplify it if you want, but really even if you leave it in this format, it should be perfectly fine. So a and b are constants that we actually determine. B is 1 and a is this rough looking expression. But yeah, so that was essentially the value of p of x, right? Once you found a and b, you just plug it back into the equation of p of x that we found over here, and that's it. That's how you would solve this problem. So it's actually pretty simple if you knew this lemma, which we just proved as well. If you actually knew this, the lemma and its converse, you can actually prove that this problem then becomes very trivial. However, if you do not know this lemma, if you, let's say, went to the exam without knowing it, is there another way to solve it? Yes, there is. Using maybe it's a little bit more rigorous, using maybe some ideas of number theory. Maybe you can apply Chinese remainder theorem, etc. But I would definitely advise you to have a look at this theorem. And actually it's actually very standard result. However, we might not see it regularly across a plethora of Olympiads. But I really hope you enjoyed that explanation. So moving on, we have certain book suggestions for calculus and ISI my entrance exam, Pre-calculus by Tarasov, Single Variable Calculus by I.M. Maron, Playing with Graphs by Arihant Publication, Challenges in the Pre-college Mathematics, Mathematical Circles, Excursion Mathematics, and a test of mathematics at the 10+2 level. So after that, we have a similar but challenging problem, and it's asking us that let Px be a real polynomial satisfying three given conditions, P of 1, P of 2, and P of 3, and we need to determine the remainder when P of x is divided by x minus 1 times x minus 2 times x minus 3. But the really obvious hint over here is that they've given us P1, P2, P3, and they've asked the remainder when x minus 1, x minus 2, and x minus 3 divides P of x. What's the remainder? I think you might have seen such problems before, especially if you're preparing for like IOQM. This is one of the rather standard problems, and the IOQM is coming up as well. So if you're able to make any progress on it, or if you're able to solve it, let me know in the comment section below and I'll help you out. Until then, I'll see you in the next video. Thank you very much and bye-bye.
Cheenta programs are designed for students who are passionate about mathematics. And they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.